You guys want to get started? Looks like we can get started. It looks like there's a couple people trickling in, but we get going. We got a great event tonight. This is the first event like this. I think we always intended that there would be more events like this, so I hope that this is exactly the type of event that we'll be planning in the future, and that it's a more open discussion and a more open dialogue with everybody who's here, because I think it's a really good group. We always have a good kind of mingle before and mingle after the meeting, so I think that's hopefully we can extend some of that dialogue into the conversation that we're going to have tonight. The idea for this started, actually like one of the first computation events that we wanted to have featured the work of the kind of cutting edge academic groups within the city, try to understand how they are engaging the subject of computation, parametric design, and digital design, and have them really talk about that, because I think that it's really, in a lot of ways, it's shaping the way that the younger staff within our offices are coming in and synthesizing information, but it also is a big, at least for me and for our office, I think it's a big, the idea that there's parametric design and computational design that's informing what the design process is again, it's at the hands of these educators. So the idea was to get kind of a big panel with representatives from every school in the city. It turns out that these guys are the most interested in doing it. So we'll try to kind of follow up with people from other schools, but again, these guys are really excited about doing it. So we have Tristan from the School of the Art Institute. We have Jordan and Thomas from IIT, and they're going to talk about their studios and their research that's going on in their representative schools for a few minutes, and then I think we can open it up to a more panel type discussion. I hope that everyone here has some good questions and we can get into some good discussions about it. So thanks, guys.
The competition guys have trouble.
Oh, is it flying off the screen?
Okay. So my name is Thomas Kearns. A year and a half ago, a little over a year and a half ago, I was appointed the Director of Design Communications under the new administration at IIT. In that position, I've been charged with essentially refactoring the entirety of our curriculum as it pertains to media, visual communication, drawing, modeling, and then as a result, computation. I have a background in architecture, of course, but I also have a degree in professional practice in software engineering, which I bring to bear on the development of this curriculum. Interestingly enough, the sort of first and I think most important decision that I made was that we were going to spend a lot less time teaching computation and a lot more time critiquing work on the wall. And the reason for that is that I've been teaching at IIT for nearly 12 years, and the thing that became apparent to me very early was that the majority of these classes are really oftentimes taught by technicians, many times aimed at building technicians, and that was doing a great disservice, a kind of detriment to the curriculum at large, to the design studio and the other courses. So I'll talk a little bit about the 4-course required sequence, and Jordan's going to show a lot of work. So we're actually going to spend less time talking about our advanced research and more time talking about the foundation on which we're trying to build future research from our students. So what that involved was basically pulling back, changing many of the staff, getting people who maybe weren't computational experts but were really good designers and really good teachers to come in and participate in this dialogue, critical thinkers. So part and parcel with this change in administration, the dean launches this publication, Nowness, which is intended to define a kind of global direction for where the school's going. And of course, we're all wondering what the fuck nowness means. And still many of us don't know. I mean, you can look at something like the Gartner hype cycle to see like what is nowness with respect to computation and technology today. And I've highlighted the areas of this that I think we're trying to tap into in various parts of our curriculum. But for me, that really gets summed up in this idea that what we need to be doing is not making tool users, not creating a curriculum that builds tool users, but creating a curriculum that can facilitate the development of tool makers. You know, I think I have a deep suspicion of our software tools and the kind of opacity that they present to our students, where they're not really always so aware of the kind of constraints that these softwares are imposing on them, right? And we get kind of mannered design processes a result of the software. And so, for me as a software engineer, I feel very strongly that, and not just our architecture students, but I would say like my third grader, I would put in the exact same camp, should really all also be learning how to be computer programmers. That if we really want to engage with the direction of where our tools are taking us, or define that, we have to do that. So at the core of this curriculum is a brand new 4-course required sequence that starts in the first year of the undergraduate program. There's a parallel 3-course sequence for the graduate students. It's consecutive semesters, so that they're finished with this at the end of their second year. And you can see that we start off in the first year focused on essentially the relationship from a content standpoint, or the motivating standpoint, the relationship between objects in the body. And over the 4 courses, we increase in complexity and scale. So we go from kind of singular objects and body into program, an event, multiple objects, multiple bodies, up through the scale of the city. And then in the 4th one, sort of projecting into the future of where things will go. Simultaneously, we're teaching them, we start out with individual projects, and they grow from individual to pairs to small groups to large groups, so they engage with the realities of collaboration and communication between partners. And the kind of outline of the core topics that are covered here on the right, you'll see then also from the get-go introduce scripting out of the gate into Grasshopper, and eventually into what we hope full-fledged object-oriented programming. I would say that we've kind of picked apart maybe like the first 4 courses that you might take in a computer science program, taken out what we think is really essential, and repositioned that within the architecture curriculum. And throughout this, there's an emphasis on physicality, physical media, literally making things, and then computation in the way that we all understand computation, but then also we the software engineers, ways of thinking about both describing, managing, organizing complexity. So this little box that you see on the right is something that's called a UML class. It's part of a UML diagram. UML stands for Unified Modeling Language. Use it to describe essentially the objects in their software and the relationships between those objects. So we borrow from that as an entry point about information modeling without having to actually teach any Revit. We don't teach Revit at all in the school. I should say at all. Joel's got a little bit of it happening, but we've basically taken it out of the curriculum because we see it, especially in the early students, a detriment to what they're trying to do at the design studio. So instead, we talk about information modeling out of the gate. We do it in a conceptual way. We do it in a way that's maybe a little bit more analogous to a kind of burgeoning area of philosophy called object-oriented ontologies, which grows out of speculative realism. So there's a whole area of philosophy now who are leveraging these ideas of software development in order to understand the complexities of the world. And we introduced that to be able to talk about both the semantic understanding of what things are and how things relate, but also the kind of topology of things in the world once they kind of instantiate themselves. What we try and do, what we hope to do, is by introducing these techniques, we can have a very critical, almost philosophical dialogue simultaneous to talking through media and with media, in some cases, these two diagrams and mapping kind of things start to converge in kind of interesting and more unpredictable ways. And ultimately, the goal is, this is from a studio that Jordan and I taught this last spring that dealt with, urban data, agent-based modeling, and simulation. This is happening in the final year of the curriculum, and this is with a group of students who are into this stuff and have taken it upon themselves to want to engage with it, and two great professors to help guide them through the way. But the hope would be that once the students who have entered into this new curriculum get to the 5th year, which will be a few years from now, that everybody will be able to engage with this and to use the technology not necessarily in conventional ways. I mean, we're using it here to sort of interrogate practically and theoretically the way that the TIF system works in our country, and how it engenders urban development. Maybe that we can change that to be more productive and to be more data driven. And at the same time borrowing from Constance New Babylon. So there's this kind of interesting dialogue of theory and application. So that's my goal. That's what I'm trying to build a team. Have a number of the team members here, and Jordan's played an instrumental role in both the advanced part of it and throughout this corporate sequence. So I'll let him describe that.
So my background, just by way of an introduction, I did my graduate degree at SciArc, and then spent a number of years in China at MAD. So computation was sort of present in my practice leading into teaching. And then when I was planning to move to Chicago a year and a half ago, with really no connection to Chicago, I sort of got connected to Thomas one way or another, and sort of realized some of the things that I've been trying to do in China in terms of urban scale modeling. He was already 4 or 5 steps ahead and was starting to institute this this new curriculum. So it was a really fortuitous thing. I sort of got on the ground floor of the development of this curriculum, and so I've taught now the first iteration of the first 3 semesters of this 4-semester sequence. So I've sort of got a on-the-ground perspective of this and what our approaches are. Hopefully this will let me proceed. Okay, so design communication. I think in general, just sort of having this opportunity to go back over what we've done in the last year and a half and thinking about this name, design communication, I think something we have to consider now in light of new technology is communication with what or with whom. Obviously, the architect has always used the drawing as a way to communicate to the builder or to the client or to themselves. That's sort of that relationship between the production of the drawing and the building has been an important thing. But as objects become, as we begin to conceive objects, not only with attributes, but also starting to think of them in terms of having behavior, and as the tools we use become explicitly linked, we have to start thinking about communication maybe with non-human actors as well. And so something interesting, I think, that pops up as we look at these classes. So I'm just going to walk through, as Thomas said, this is the first 3 semesters of an undergraduate, sort of introducing them to the tools of the architect from zero. So these are 18-year-olds. And we started this first project with students looking at what we called intrinsic and extrinsic movements of everyday objects. So asking them to explore how an object internally moved and how it might move sort of externally as part of its use in relationship to the body. And so through the development of these models, students began to identify the sort of constraints of that movement, what can change and how. and started to set up a sort of set of instructions for how to control those things, which led us sort of by the second half of the semester to start a conversation about how to translate these rules into a set of scripts. And so really with really basic, this was done in Rhino, and with a really basic introduction to some very, very basic, starting with them just being able to describe explicitly how these objects move, what are the constraints of that movement, and then be able to translate that into a list of instructions, and then to be able to write that list of instructions using Python coding in Rhino. It unlocked the potential for students to operate with control over a much larger set of objects or over a much larger set of time. So really all we introduced in terms of Python coding was the idea of the variable and the loop. So the ability to control something that changes and the ability to create repetition. And then sort of a slightly more advanced take on that, the idea of the nested loop, that if you put a loop inside of a loop, that all of a sudden you can create, or loops inside of loops inside of loops, you can create arrays that start having multiple dimensions. And so this becomes a really sort of immediate way for the students to start engaging with both the control of their object and this idea of scripting. And so various students sort of took this in a lot of different directions. Some more interested in the movement of the object in the real world, and some in more kind of abstract representations. But you know, I think this idea of where the drawing resides in this, it starts to shift and become a little more problematic. I think, like, I wouldn't argue that the script is a drawing, but I would say that the result isn't necessarily the drawing either. That it exists somewhere between these two things, and so our task going forward becomes to think about ways to represent in accessible ways the sort of intelligence that's embedded in this case, really simple scripts. But as these things get more complex, the burden continues to be there to be able to represent these things. So that was the first semester. The second semester, we tried this shift from both from the digital to the material or the physical, and the idea of this shift from what Greg Lynn, Deleuze, and Carpo have described as the shift from the object to the objectile. And I think that's captured in a lot of ways in this idea of the class diagram that Thomas spoke about. So the objectile is a notion that it describes, rather than describing an object directly, that you describe a sort of a family of possible objects, of related objects, and you control the attributes and behavior of that family, and then from that sort of classification, you can produce a sort of infinite number of related forms. So how do you start controlling that kind of thing? And so this is this example we use all the time at IIT. I think it's really useful, the Richard Serra project to lift, to get them thinking about, when you're thinking about modeling from material immediately. So when we ask how do we model this, we say, well, start with what Sarah started with, and to think about what are the attributes and what are the operations that can be used, and that leads directly to a kind of system of classification, and that the relationship between the operations and the attributes begin to define what can change and what has to stay the same. And that when we think about modeling this thing, and we start thinking about using construction geometry as a way, and history in Rhino as a way to control this directly. So we can start to make not just one object, but a whole family of objects that all sort of operate according to this basic system. And so really thinking through modeling as a set of operations that that relate to the material form, and that that there's this relationship between construction geometry and the jig, that construction geometry is what controls what stays the same, and what can change and how it can change. And so we can it allows us to produce a family of related forms with the idea ultimately that, and in this case we sort of unleashed the Shapeoko CNC robots, that the translation here is ultimately between the student's 3D model and a machine that produces a physical form. And I think that the long-term ambition, that we really struggled with these machines in a lot of ways, but the long-term ambition would be that perhaps every student would have one of these on their desks and would be able to fabricate and control these things directly and immediately. And then the third class, which in a lot of ways for me has been the most exciting, and which we're working on this semester, addresses the relationship between city data and objects that occur in the city, and start to ask, can we make explicit connections between these two things, and begin to drive the formation of objects in relationship to city data. And so, what we've talked about with students is, starting from, obviously in Chicago, we have access to an incredible amount of data through the Chicago Data Portal, but that for any serious question about the city, there is no perfect data set. And so it becomes the responsibility of the student or anyone working on these maps to be able to integrate multiple data sets, whether those are coming from the data portal or things that are being collected on the ground, and to be able to connect those things together in an intelligent way. So, like a lot of maps that you see, IIT, particularly in the fifth year in the Cloud Studio, which has a sort of has an agenda about the metropolis. We see a lot, and a lot of them, the sort of first pass of these maps focuses on, or is the result of a kind of layering, and so sort of it suggests relationships through transparency, basically, which can be quite evocative. But what we were interested in this class was to give the students the tools to be able to make those relationships explicit and measurable. So how do you make a connection between thousands of crime scores and CTA stations? Or how do you link a data set that that talks about the ridership of a CTA station to the actual geometry of that CTA station, and then begin to develop operations from that? So this becomes about engaging data, and it brings us back again to this UML diagram. So these UML diagrams have been really useful for us throughout, and a sort of common shared notational language that I think all of our students will now have. So thinking about a manhole cover, thinking about what are the really key attributes describing that, and then thinking about how some of those attributes might help us to make links between other objects in the city, that we might be able to make explicit connections. What street is that manhole cover associated with, or what institution? And some of the work the students have been doing, I think getting back to that idea of the difference between the written out script and the final form, that the intelligence is somewhere in between those. I think we pushed really hard with our students to get them to describe in explicit terms what are the operations that they're doing to produce these maps. So I think one thing that GIS software opens up this potential for really anyone after sort of a weekend of work to produce really beautiful looking maps, but they can be really beautiful but complete full, or really beautiful and really intelligent, and it's really hard to tell what it is. And so we think that it's it's essential, and really where the criticality comes, or how we evaluate these maps is not on the thing on the right, but it's really on the thing on the left. The way you describe the kinds of validation that you did and the kinds of normalization you did to arrive at this pretty color-coded map. So we can't evaluate the thing on the right without seeing the thing on the left. So that becomes integral to the process that we ask the students to do. Another group of students who were looking at trying to evaluate the cultural boundaries of Little Village by the colors of the house. So they went out and cataloged the color, the brightness of the color of every house in this neighborhood, and then generated this. So by integrating building data and this survey they had done, they were able to generate this map that starts to tell us some kind of story about the city at a more nuanced level than maybe we could have known otherwise. And then going from there, starting to map out specific urban objects and understand these objects both as 3D models and as sort of GIS objects, and being able to try to start making links between these. And continuing to think about, this is a sort of larger class diagram, the sort of compositional logic of these objects, both going down in levels of detail, so down into the nuts and bolts, and then also up in levels of detail. So what are the larger systems that these objects sort of fit themselves into? And being able to map those out in these larger class diagrams. Again, as a sort of integrated graphic language, another one where we're sort of integrating the class diagrams with the 3D models and renderings of these objects. And then where we're sort of heading with this is to start to make an explicit link between the city data and the 3D model through Grasshopper. So something that I'm really excited about, actually Joel, who's sitting right there, has really spearheaded this, is the development of a plugin for Grasshopper that lets us import GIS shapefiles and to Rhino, or to associate Rhino objects with GIS attributes. So we can now associate directly attributes with objects, and we can also start to drive parametric models of three-dimensional objects with city data. So this is one student starting to diagram how this process might work for a fire escape, that he would, using GIS data, be able to predict which buildings in the city would get a fire escape, and then begin to evaluate how many people are on each floor of that fire escape, and then begin to drive where on the building that fire escape would locate relative to the floor heights, and how wide the fire escape, or how many of the fire escapes need to be placed. And this would all be sort of linked in an explicit way through this sort of mix of GIS and Grasshopper modeling and parametric design. So, so yeah, I think that in a way this sort of brings us full circle back to the object, but now we have an object that is linked to the entire city, which is something I think is really interesting.
And the fourth class comes in the spring. So we because of the change in the curriculum, the first group of students entered in last year. They did 1 and 2. Now they're in 3, and they'll go into 4 in the spring. And we've had the first opportunity to go back and redo the first course, and things are tightening up nicely.
Okay.
And we don't allow our students to produce any Grasshopper, show us any Grasshopper wiring diagrams.
That's right.
It's absolutely forbidden, because it's a huge problem in school.
Oh, do we have the same thing going on here?
Should be. They have a,
I might have a FireWire version of this. Do you have a FireWire version of this? Ah.
really?
Do I? Yeah, I'm pretty sure.
I think you do.
It's a FireWire one. It's new. Can I? Do you have do you have Keynote?
I think so. Yeah. Don't they always work? No. No, I don't. I have PowerPoint.
Okay. Well, I've got some. Does anyone have a Mac adapter? Yeah, for FireWire or for like a FireWire video? I'm pretty sure it's. Well, that's a downer. Sorry. Let's try. You can. I'll hold it up. Which is lots of material work here.
Save it as a PowerPoint.
Maybe you can just do some grades.
I can PDF it. I can. Or can I save it out as a PowerPoint?
Yeah.
How do you do that? File, save as, export to PowerPoint. Yep. Yeah, go get a beer. 5-minute break. Get a beer.
I know there's one very
Okay. Thumb drive. Oh, this is embarrassing. Okay.
So you got
I'm excited for that.
You've got USB. Right?
What's it?
You've got a USB.
Yeah.
Principally, that drawing of the staircase, I had to look at it. Talk to them about that. Yeah, it's like staying out. Reported me through all the construction documents. One line, right? That's right. It's like mandate. You can't understand the drawing one line away, and the drawing wasn't drawn very. I did have to write a little script for Illustrator to be able to change all the line weights uniformly, like increase all the line weights by double uniformly, because you have like thousands of different line weights. So I didn't create that. Yeah, you could, like, that would be one way to do it, but need to like scale it.
You don't have a FireWire adapter, do you? Video adapter?
And then scale back down or something like that. But it was really heavy drawings.
You have PowerPoint?
Yeah, I think it's open.
Can I try dumping this on yours?
Yay, wait.
How do I,
You already have this, right? So
is that FireWire?
no, that's not okay.
Thanks so much. That's cool. That's right there. No, just
Yeah, that might help.
let's just do a test. How do I play this? Oh, let's do it. Great. Okay. How do we rewind this? Okay. Right. Very sorry about that. So, SAC is a really different place. We have a very new architecture program, and it's located in a school of art. And what that means is that the people who we bring to our school and the people who are interested in being there have a very different way of thinking. And they usually come from practices that are much more diverse. I mean, they're not coming from, we have engineers, we've got aerospace engineers coming, we've got sculptors coming, we've got performance artists coming, and they all come to our program to form this really unique group of people who have very, very different ways of looking at the world. And what better thing for a school of architecture? So I thought I'd do a couple of things. I thought that it would be useful just to show you a little bit of, give you a little bit of a taste of the sorts of things we do. And these are all pieces of work from my students. Because we have different types of students, our faculty also often bridge many areas. And so I teach primarily in architecture, but also teach in fiber and material studies. I'm also just about to teach a course in fashion. I teach in sculpture. And all of these things actually are really quite influential, because as architects, we like to think that we know a lot of stuff. And we do, but we tend not to be as broad or as diverse in our thinking as possible. And if we think about education and what education really means, and if we ever have a discussion about education, what we really are talking about really is the future. Right? These people who come into our programs and who are there to learn and study and grow, really, they're there for tomorrow, right? Sure, we have everything in the past, right? We've got Mies, we've got, no offense, really. I love Mies, I really do. We've got the past, but, all of us in this room are not here for the past, right? We're here for tomorrow. And what architect isn't here for tomorrow? But tomorrow is this unknown territory, right? It's a place that, we don't know, like what the methods are going to be. We like to think we know what they're going to be, but we really don't know. And we're designing for people who are radically different from ourselves very often. You think about the practice of architecture today. Like, who here is just working on buildings in Chicago? Or maybe the better question is, who actually has a building in Chicago that they're currently working on, right? I mean, that's like the minority these days. And, well, okay, maybe we've got a certain type of crowd here, right? We're talking computations. We're usually talking big offices. We're not talking little offices out, But, I mean, we're really quite sort of, as a group, quite myopic. So when we're talking about, building a school of architecture and what's important, sort of this diversity is critical. And we also have to remember that really, we're just lighting fires. Our role as teachers is here to help someone find where they fit in this huge spectrum of things and work out, like, what direction do I want to go in? So, oops, okay, that's repeat. So I don't know Microsoft that well. Where's this mouse? How do we go? That's next slide? Perfect. So, as an overview, I just thought I'd give you now a quick sample of like an undergraduate studio. So this is an undergraduate studio that I taught 2 years ago. I'm a fairly new faculty member at the school. In the studio, I had students. It was a very small studio. It's maybe one of the privileges of SAIC. I had 5 students. Yeah, 5 students. Usually studios are bigger than that, but I had 5. Maybe because I'm a new professor, no one knows me. It's like, that crazy guy. But so this was a fashion student who came into architecture. And they were all very, undergraduates, second year, really the first. So they don't have tradition, right? And so one of the big things that you start to teach them, and now computation and the future, but one of the first things you have to start to do is give them like a little entry point. And this is deeply computational. I mean, this is Fry Auto. So one of the ways that we teach, and we also teach from a very embodied way, everything is material, right? You really need to be material if you're at our school. So one of the methods that we use is sort of a method of adoption, like we adopt methodologies, again, Fry Auto. So here's an undergraduate student in the second semester developing methods, really sort of starting to copy Auto, but to try and find a way into the profession. And of course, we're talking about sort of tensile structures, minimum surface area structures, right? Like how do you produce things efficiently? But things that are not just efficient, but also beautiful, right? What do architects love? We love, if there's one thing we're really about, like form is it. So I think at SAIC, and so bubble studies, right? Soap, skin, film studies. Computation at SAIC is something that might seem a little bit foreign, like we're in art school. Why would you be computing things? You're using material. But it's a sort of place where you find people, like today I was in, so one of the classes I teach is in fiber and material studies. And there's a department, and there's a MFA graduate student who is there building machines to braid, right? And sort of using like, so machine is an algorithm, as a physical algorithm to produce material, and material that has certain behaviors. So often we think that things result in this type of form, and for architects, largely it does. But you know, for artists, computation might very well result in this form, which is, I mean, this is Fry Auto too, right? But it's not Fry Auto as a building. This is plastic being melted to produce tensile surfaces that are sculptural for a particular type of sculpture. And we also use then, if you think of computation and material and performance, the other sorts of things that we touch on then are the emergence of intelligent materials and how material processes can actually become computation themselves. So this was from a designed object student who was taking a course in fashion, one of the early course that I taught, who was very interested in taking the torso, scanning the torso, simplifying the scan, and starting to produce garments or clothing from this geometry, and then taking the sort of understanding a little bit about the methods of crafting the garment, applying things like thermosensitive dyes to fabric to end up having coloration that is affected purely by body heat and the contact or the relationship between geometry and the body. So deeply physical. Other students who come from drawing, starting to understand notions of balance and tensegrity and structure, admittedly very alternative, but actually deeply computational. And then we end up with other students who produce, who are very, I mean, form is not just an architectural thing. Artists love it too. This is a fiber student who came from painting and drawing, who ended up just producing stitched plastic. So this is plastic being stitched and being melted. But you know, this is very much also a lot of what we see in architecture today. The role of computation, though, is then very interesting. If we can do these things that are sort of computation-like or using material for computational purposes, we then sort of have to ask, well, you know, what is architecture? And what are we really starting to do as architects? And this is some of my work, just prototype work. It's the first non-student thing you've seen. But I think one of the things that we end up getting, well, where we go at SAIC is we start to say, well, computation as a material then must be applied to very specific classes of things in which solutions that are carefully constructed balances emerge. So these are tensegrity towers, right? Tensegrity geometries are deeply computational. You can produce them manually. It's very difficult to produce them manually with any sort of accuracy. So computation then starts to adopt a very certain role in focusing formal studies. Another really important topic that no doubt we're all familiar with here in the room is energy. And I had another slide up here, but I decided to show these two instead, and just rely on your imagination. I mean, who here hasn't seen, a diagram of lighting condition or lighting or energy analysis from a building today? I mean, we've all seen them. We all know that they're typically maps, like colored maps. Right? Well, so that's one way of starting to understand or start to tie form to energy. But another way to do it is actually then again through materials. So this is a first year graduate level class that I used to teach. Now I'm no longer teaching it, in which we taught construction and energy together so that the logic of construction is tied fundamentally to energy. That's actually a very easy thing to do these days because energy tools, you can think of Ecotect or Design Builder, any of these tools that you use. Construction is simplified down typically line work and surfaces, and you can query a surface or a line very easily to understand a much deeper construction logic. Right? This is frame construction, this is masonry, this is whatever it might be, and start to understand energy. So we do teach that, but then we also teach energy this way. So this is a prototype in which the students are tasked to keep a liter of water warm for as long as possible, right? And we get the class to define what warm is. That's one of the challenges. We say, here's a problem. Now we need to work collectively to solve it. And it's a very interesting way of working because all of a sudden you task the student body with not just understanding not just producing a solution, but actually, which is kind of what you guys are doing, but we're doing here in material. And the beautiful thing about this is all of a sudden you get students looking for solutions that you would never think of. Like, okay, can I make something that's completely natural, right? That has like no, that's absolutely organic or uses as natural materials as possible. And you can give them access to information like the embodied energy of materials and something like the ice from the ice manual from Bath, the University of Bath. And all of a sudden they can understand that they're producing something that has an embodied energy of 50 megajoules. Right? Do you know what 50 megajoules is? Really? Do you know what 50 megajoules is? Come on, Les. Well, so one way of starting to understand this, and I think this is the approach we have at SASC, is you can break that down to, and do we know what a calorie is? Do you have a sense of how many calories you consume per day or something like that? Do you guys watch that stuff? Yeah, I mean, okay, so there are relatable ways. You can say, well, how much do we consume in our diet? And then how many days of energy would this be if you ate this, right? And all of a sudden, you give students a really very tangible measure on the importance of making a good design decision, right? Because here's another quality of students today, and it might very well be, it's no doubt in all of us, they are here because they want to make the world a better place. I mean, they really do. Like on the first day of class, if you put up, you get them to raise their hand and say, what are you here for? They say that is the leading thing that they want to do. So stuff like this really matters to them. And so teaching, I think from the SAC position, is deeply about computation, but providing very simple means for students to access that in a direct way so that they know they can actively measure their own decisions. And what is more computational than that? Here's an example of some current work. So I've got two students working in my current studio, in which we've had a very open topic of housing. And again, the students have defined really their own studio problems. This is a third semester studio. And this student said, I want to understand how to produce minimum energy buildings through studying surface, the amount of energy moving through surface. So he developed a genetic algorithm or processes that relied on genetic algorithms in Grasshopper. So to then start to model or produce methods, a method for him to start to produce this work, because he thought it was really. But where's this really going? Certainly we all know about optimization, right? We all know about these types of processes. We probably do it ourselves. If we think about sort of where computation goes, certainly it's going to exist in design tools, right? And we're going to be producing design tools. But perhaps if we really look forward and we really think about where students need to go and what students need to do, they need to understand that computation is no longer limited to this thing, right? And we all, again, this is just stating the obvious, right? We all know that computation is no longer in a computer. It is bound into everything that surrounds us, right? We have, Nike's producing like, stuff in our shoes, or they used to, they don't anymore. It's in our, like now it's all moved to this, right? This measures everything that we do. It knows when we sleep. So that is ultimately where architecture is moving. So the deeper challenge to all of this is not just to look at tools, but to start to understand how we can instrument form to produce form that is intelligent and that can make decisions for itself. So we're talking about control systems, we're talking about embedded algorithms, and we're talking about, this will be the last slide. I'm going to skip over this. This is just an optimization thing. This is more interesting. This is dynamic optimization, where, this is just around the corner, but imagine if you could have a building that could start to adjust its shape based on all of the data it's collecting. Like, what can a building do if form is taken out of the hands of the architect and put into its very being? I mean, it seems a little bit crazy, but it makes so much sense. So buildings like this are, I mean, they are certainly in the future. We don't have them today, but they're one step away. If we can have a thermostat that can control the temperature of a house, and we know that the primary interface between the house and the environment is its skin, right? Certainly we can have intelligent blinds, but what else can we do? If shape optimization is really important, and we spend all of our time as architects doing shape optimization, why can't we get the building to start doing it for us? So that's all I have to say.
Well, thanks, guys. It was a good talk. I think it'd be good to have, if anybody has any immediate questions. I have tons of questions I've been writing down so I can get things started if that's okay. But it'd be good to have an open dialogue here. So, you guys want to talk a little bit about you used similar terms for sure about like I think you used the term broadness of thinking, and I think that there's that you're actually teaching something different about how to be critically thinking about the things that people are making or the things that students are making. Can you talk a little bit about the critical, have you seen an increase of critical thinking and how values are attributed within design studio problems then based on a different type of, methodology of teaching?
Yeah, I think one of the big problems in teaching computation at school today is the stuff that everyone wants to do needs typically to do it really well. Needs students need a lot of other knowledge, right? So if we're talking about performing or getting students to start to produce optimization, and so Sergey was, who's in the middle there, is one of my students. He did the tower stuff. He's done really very well, but in terms of like just running at a problem and tackling it. And he's one of my first students to do that. But it's really difficult actually, because most people want to leap in and they want like structural optimization, they want this, they want that. But even to just produce an algorithm that will give them one structure, actually they're very close to being able to perform optimization. They just need to incorporate analysis into it and produce it, like run it through an algorithm. But that's a huge bucket of knowledge for them, and they've only got 3 years at school. So I think there's a problem with knowledge, how knowledge fits into these processes, which is, I think, why we take sort of a more direct approach with them being able to build knowledge, like through understanding like energy in a very direct way, for example, or structure in a very direct way.
Yeah, this idea of immediacy, I think, is essential to it. The more you can move the students towards, and the more immediate the problem becomes, then whether it's a problem of heat or a problem of geometry in trying to relate two different geometries across the city scale, something in terms of these little diagrams that we've had them draw, forcing them to describe their process opens up a conversation with them where we can start talking about how do you validate each of these steps? How do you made a decision here about how far to buffer a building in terms of associating crime to that building. You chose 100 feet. How can you validate that in relationship to, how can you make sense of that? And so, going from, it really just starts a conversation, I think. Yeah. But it starts, I think at the scale of the map, it's easy to produce these maps, but when you start breaking that map down into a set of operations that's happening at the scale of the building, then they can start to bring their own value structure into it, and then you can start having a conversation with them about that value structure and how they can start articulating the value structure in their work.
Yeah, and the value structure is really difficult to get at, especially when you factor in that these are 18-year-old students who have more or less been programmed in their education to look on a kind of narrow path, to follow a set of instructions. They can do that really well. But when you pull those instructions away and open it up, they're left with, like, I don't know what to do. I think that's our greatest challenge with these students, to get them to the point of criticality, is simply to reteach them or open them up to ways of looking at the world, right? To how to see, to how to listen, and express what their value system is. They have no idea what a value system is. So I think that's what we're trying to do. That's what we start by looking closely, and by getting them to talk to each other in the class, get them to teach each other, rather than having us simply be there to give them an algorithm or a way to do it.
Yeah, I think that they all come with values, and I think actually they're really good values. You just have, I think the trick to teaching computation is just showing them how to start to unlock. I mean, really, it's a question of unlocking that, getting them to look at the world in a certain way. Like that example of the student who did the cocoon thermos, right? He, that was 50 megajoules of embodied energy in that model. Well, 50 megajoules of embodied energy, if you work it out on a 1,500 calorie per day, which is fairly high. It's like at your active per day. It's like 8,000 days. That's 8,000 days worth of energy, which is a lot, right? And so all of a sudden students start to understand these things, and then they know what to look for. And as soon as they know what to look for, then they can start to think, well, if I know this is what the goal is, then they can start to imagine what the algorithm might be towards that goal. The problem or the hurdle I think education has to face in the compressed 3-year format, which is really what we're in. Like a graduate student comes in, okay, 4+2, right? I'm mainly dealing with graduate students, but they come from everywhere. I've got poli-sci people, whatever. So they don't have that, that basic design background most often. But it's fueling them up with that other knowledge so that they know that they want to make something that has this outcome, but to get them there is really difficult because they've got all of this other stuff to navigate. In a certain way, it's actually really good because you can then say, well, you need to know about this. And then the really dedicated students go off and learn it. They say, oh, okay, so all of a sudden they've got a reason to study structure. Right? It's like, wow, if I study structure, I can do that. And that's pretty cool. Have I spoken too much? Yeah, I mean, I think it's I think education today is a really different beast than when I went through school, which wasn't that long ago. But I mean, I wasn't exposed to any of I had professors who built computational tools, but I never built one myself. And I think now, at the point, thanks to David Rutten and all of the work that he's done with Grasshopper, now the emergence of Dynamo, where actually these tools are really, available to students. And even, the nature of coding today is like, it's actually quite simple for a student to pick up Java in like processing, for example. It doesn't take them too long to do it.
But I think like, taking Grasshopper, even for the students to understand that the processes the sort of geometric processes that underlie a lot of these tools are pretty accessible to them when you start looking and you sort of breaking down the geometric operations at play, and it's just they're being multiplied. They're being automated in a way where lots of them are happening at once. But if you look at the basic principles of like a flocking algorithm, geometrically it's really relatively simple if you understand a little bit about vectors. And so I think getting them back to being able to describe the geometric steps that they need to take, even if it's a relatively simple thing that they accomplish, that they can describe explicitly step by step what the geometrical operations were, gets that, and then they can see that this component in Grasshopper that has some inputs and some outputs is actually really just running through a list of instructions that it demystifies it in a way, and it I think empowers them to start breaking these things apart and rewiring them in ways that will surprise all of us. And so, but also, making parallels between something that's happening in the material world and it's sort of analog in the digital world. It's an empowering thing for the students.
I think there's another really interesting thing that comes up, which is how to build the right type, and even just really simple things. So the right type of method, right? The right type of process. One of the great things you can do with tools like Grasshopper that becomes very clear is you can show them very quickly the smart way to do it and the dumb way to do it, right? And the dumb way to do it is to basically build sort of, well, we all know this, and we've all run across this. Build an algorithm that, is basically got stuff in, you got one thing coming out, and then to duplicate it, or to have like two things come out, you need to duplicate that entire algorithm because you built it the wrong way. Like you've not put in the right control in there. So things like Grasshopper actually work really well to get them to change the way they need to think about structuring problems as well. But you have to show them kind of the impact of sort of the not so clever way of doing it first.
And something that's been really a nice moment for me, sort of three semesters into this process. Just that the really basic sort of introductory Grasshopper tutorial, if you will, about producing a grid, and this idea of how data flows and how by enabling different structures, data will flow in different ways. And so the sort of relationship of the way you need to think to understand that basic idea about Grasshopper is basically about choreographing flows of geometric data is really the same thing as thinking about how you would structure a spatial join in GIS. That again, it's just about matching up two different lists of data in an intelligent way. And that's really the same as running a loop inside of a loop in Python. So it's sort of re-encountering these things first in a really simple way. And then by the time you get to Grasshopper, you understand that really under the surface, it's the same thing. It's just about sort of directing lists of data into the appropriate, in the appropriate way, sort of choreographing that. So that's something that when, I think for the students to be able to grasp that empowers them again to use these tools to make them do what they're not just being handed them, but actually take control of the tools.
Do you think that then helps them synthesize more complex design problems, or is it really skewing the way that they're looking at those design problems? You know, I think that it's good because you're not trying to pack the knowledge into that 3 years. You're actually trying to teach, process of acquiring knowledge and synthesizing data.
I think the best design problem or the best solution for design is the simplest one, right? So I would actually say that, one way to tackle the complex design problem is to say, well, it's just a bunch of simple problems, right? And if you think about simple problems in the right way, you can actually get a very powerful result. And I think, things like sensor data, or starting to use sensors directly so that they can see that, whatever physical property that they're measuring so they measure this. They measure the weight of this, for example, or they measure the amount of light coming out of here, how that can propagate through a system. And I think there's something really nice in, I don't know, there's something really nice in being direct and saying that, listen, if you develop one module, and actually this is a very Miesian idea, if you develop one module that does this thing in a certain way, it can have, a very profound output. And then you're really talking about mass, like the production of things on mass, like a repetitive unit, right? And a new type of sort of modular design in a certain way. That's kind of where you go, but that's one place where you can go with all of that. So it's kind of actually tackling complexity through simplicity.
Well, and the idea that we were just talking about of valuing and teaching a value system based on that is I think what emerges when you talk about optimization and teaching optimization. And what's I think sometimes interesting is when it's two different variables, we'll see two different optimizations, and sometimes those are contradictory, right? The energy and minimal surface, geometry has a very different, it can be in opposition to something like program or building. So when you start to oppose things to each other, it forces you to kind of choose what those, what you would value. So it's kind of it's an interesting thing to then try to have someone explain, you're tackling a very complex design problem that you're forced to negotiate and reconcile, and by reconciling that reveals your value structure.
Yeah, but I think there are very simple ways to do it. You can normalize something. So you could say, well, you could do two things. You could say, well, here's the idea of a constraint, right? You could constrain something and say, when you look for solutions that meet this minimum or that target, you could say meet a minimum or that target this minimum, right? And you've got a penalty for moving either way of it. So if it gets too big, that's no good. If it gets too small, the algorithm's dumb, so it will look for every solution. But where it goes depends on how you kind of design the algorithm. But that's very simple, actually, to resolve is, I don't know, in my humble opinion, I think it's simple to resolve these things. But yeah, I don't know.
We're not, I would say, certainly in the DC core, not in the studios that I'm responsible for, do we deal with these issues directly. I mean, we're really engaged with questions of controlling a process. And we use the UML as a way of introducing students to a way of looking to sort of extract potential, extract properties and characteristics that they can work with. And much in a way of like bracketing, taking a photograph and bracketing and then going back and picking, which ultimately leads to some of these genetic algorithm optimization ideas. We're trying to use it to help them find interesting combination. And I would say not so much in a computational way, but in a I don't know. I guess it's computation. It's logic, programmatic thinking. The UML diagram exposes things to them that they can't normally see and that they're not aware of.
We remove the how-to. We never get into the discussion of what to click and where and why, or into the into the nuts and bolts, or ultimately because it's going to change, right? It's always going to change. So, like for instance, I have the misfortune and the fortune of teaching Revit, but not teaching Revit, where we actually deal with this idea of competing objectives, right? So that class looks at view, it looks at solar gain, and so how do those two are actually always competing, right? And so we deal with that through diagrams, not through, I guess, directly interfacing with the tools, but I think it's more of thinking. How does this think about this? And if we can give them the tools to think through it and not specific methodology to think about it, then the solutions that they come up with, I think, are much more universal.
Well, thinking is a really interesting thing, though, because I mean, you can use a genetic algorithm to pose problems that you then have to reverse engineer. Like, and that's another really interesting thing about computation. I mean, now we've got these tools that are people can very simply use in combination with like tie form to analysis and run it through a genetic algorithm, right? So that you then drive it towards some optimal. And I mean, one of the things you have to do when you do that is start to say, well, is that algorithm actually good?
Yeah.
Right? And so you end up in this situation where actually the computer teaches you, right? Because you have to then say, well, I started with this and I ended up with this. Like, what is going on there? Why would I end up with that? And all of a sudden you actually understand a huge amount about like designing this thing, and you can start to say, well, okay, my algorithm wasn't so good, right? Or maybe your algorithm was really good, but you have to then start to sort of do your own analysis. So it's still thinking and diagramming, but it's kind of the reverse engineering aspect of that. It's like, I've got a solution, and I think that's where design thinking is going. I don't think design thinking is, like we talk about top down and bottom up, but I think that's history. I think now it's all about reverse engineering. Really, we've got processes that are so quick and so powerful that we have to teach are sort of a student's ability to analyze a process, which is really reverse engineering, right? Like taking something apart, like maybe stepwise, or maybe just, you've got the black box, right? And you need to work out what's going in, what's coming out. Yeah, sorry, Neil.
I like your module metaphor better maybe than the reverse engineering metaphor. The idea that you would build a relatively accessible and immediate module, whether that's something physical or that's sort of a conceptual process that you can break apart and really understand and sort of build up step by step, but that it's by being computational, it allows you to sort of scale that up and go from working with one to working with a million of them, right? So, and now you've got a million things that aren't just sharing the same space, but are also, they all have behaviors, so they're all interacting with each other. But at the core, you understand what that you understand and you've authored is. So maybe the sort of grand total result is not totally in your control, but it's not about just taking a black box that someone else, you know, like an optimization algorithm that you have no ability to understand, and seeing what happens. And I agree that there's always a play between reverse engineering, but I think in ideal, like it starts with a unit that you can understand and that you can author.
Well, I think the reverse engineering thing is really useful when you are the author of the algorithm that's driving the process.
Yeah.
So doing your own verification, really. But I think it's really a reverse engineering model. It's something that we don't hear about in design education. At least I don't know if you guys hear about it, but I don't. But I think it's a really valuable method.
Is it reverse engineering, or is it? Well, yeah, or validation. I think
Well, validation
is the way we talk about
it's
it.
like you teach it spatially first,
Yeah,
in 2 dimensions, and then you scale that up to multiple
Right,
dimensions,
right,
so they understand what the process is, right? So there's a problem in my mind, actually, there's a potential problem where because these tools are so easy and so accessible that people are just clicking and downloading, that's the biggest problem that I come across.
Yeah, how do you get to clustering in the first place?
How did you do that, right? So it's, to me, the UML diagram and the thing that's in between the 2 maps is the most important thing that we should focus on, and what I think we're doing a great job.
but Thomas this is a question that I'm taking from Thomas, but I think sort of speaks to this, which is should we expect our architecture students to be computer scientists, and at what level? Like, should we expect them to be able to take apart an optimization routine? I think at some level the answer is absolutely yes, but at some level, like, we don't need our students to be reinventing the physics wheel, or reinventing. Where do you draw the line in asking these kinds of questions?
But I think that we do. I think that it's really important that I think computer science has to change. That'd be the first thing you'd say. I think you're talking about, like, and you can talk about this much better because of your training, right? But my general hunch would say, listen, we're architects, we know about the changing field of architecture, but every field is changing. I mean, fields are not static things. So we've got a certain view of computer science that itself is probably undergoing, like, massive change as well. But I mean, to that, like, if you think about, like, the power of something like the iPhone, and not the iPhone as a communication device, but as an example of something that we wouldn't have previously thought of, I mean, that we wouldn't previously have assumed that a computer and a telephone would work together so well. Maybe some crazy person would, but broadly we wouldn't think that. Well, broadly we wouldn't think that, right? Okay, we can talk about analog computing and all that stuff, but I mean, modern computing. I mean, but here's there are 2 technologies that have come together. But this is just, I mean, that's a telephone. Clearly, all of this stuff here is ripe for change. I mean, the construction industry is very soft in terms of how it's actually using computation, right? I mean, there's so much that we're just starting. I mean, Nest is like one example of an early company that is starting to actually make use of this. Google is also moving. I mean, got lots of fingers in that pie as well. But as architects, if we don't do it, I mean, I think really that's the most, like, that's why architects have to be a little bit more savvy in this. Like, using what, years ago, this or paper cup would have been considered technology, high technology. Now it's just a cultural object, right? And if we think about what computation is going to do for all of this, when this isn't just computed in the box, but it is actively computing itself, we've got a radically different beast here. So why shouldn't architects know more of that? Like, isn't data the future structure of buildings? I mean, it has to be so, I mean, these things have to be so closely bound together. I mean, they really do, right? data is informing space. Data will inform space actively. I've spoken way too much.
No, that might be a good point to.
Yeah, I would love to actually hear from the professionals what they want from the school, because we know what we would like to produce, and we hear about what professionals want, and they don't always match up. And I'd like to know whether it's hearsay or whether it's truth.
I mean, honestly, I don't think that there's anything particularly new in the computation sphere that isn't already touched on in previous design educations. I think good computational design is good design. And I think you were talking about reverse engineering versus building the module, extrapolating from there, and actually your curriculum is already that, right? You're taking the data, the city data, you're reverse engineering out of that. How do we analyze it? How do we give a critical, explicit thought process? And how do we make that diagrammed and clear so we can communicate it to the city and reverse engineer the city and understand what relationships are there? We can do that with the city or a piece of code. We could do that with paper and pencil. We could do that with the computer. It's still just good design either way. And the same thing from starting with the module, whether it's the Miesian module drawn by pencil or it's this computational module that then extrapolates. I don't think it's all that different now than it ever was. I know that I've seen people go through resumes and look to see, do they have this piece of software named on there or not. Personally, I think that's rubbish. Every 5 years, you're going to throw it out and start over again. You just need to learn how to learn. But I'm probably in the minority, and I'm not the one sitting there checking those resumes at this point. So,
yeah, I mean, the learning to learn is fantastic. What we're here to do. We could be talking about genetic algorithms, or we could be talking about color theory. It doesn't matter. Like, how do you get these guys to engage us themselves? Which I think goes back to not necessarily giving them. We have to find a way to make them comfortable with us not giving. But I think Tristan said light a fire is a really good way to put it. We're here to motivate more than we are to train. Right?
Which is, I mean, that's the thing that I think is different about architectural education maybe now than it was when we went through it 20 years ago. And I think that's what I think started this. How do you end up, this idea of the module or reverse engineering has a root in like precedent studies. It just, I think at the beginning of this conversation, we were starting with the idea that students coming out of school now are equipped with a different set of tools than what they were at the time that, say 20 years ago. And I think 20 years ago, you would have said, oh, there's a big gap between profession and education because students are coming out with the right skill set, right? They're not able to execute technology in the way that is putting buildings together. Whereas in the modern practice, at least I suspect for a fair group here, is that it's a lot of the are practicing architecture globally and have a huge influence on the design process because of the skill sets that they're actually coming to school now. So now it's even more critical that the education takes that on and says, hey, now we have a responsibility because this isn't vetted by years of apprenticeship. It's actually students are coming out with the skill set of.
But are they coming out with the skills for the tools? I mean, is Grasshopper really enabling you to contribute to a conversation about global architecture, or does understanding both the technical and poetic conditions of an envelope give you that ability to do that? Right? Like, I don't think it's not Grasshopper that enables it.
It has, though. I think in recent days, I think that it started with design visualization and the ability to render and visualize very quickly using very facile 3D tools. Now all of a sudden it becomes more.
So a few years ago we had Acadia at SAIC, and one of the people who he brought in was Andrew Marsh, and he has got a really nice way of talking about this. He says, you know, and he said this to the students I had at the time. He said, you guys are so lucky because you now have access to tools that inform you so much more quickly than informed when he was a student. And if you think about it that way, what computational tools do is they give you information, and if you use them the right way, they give you information quickly. So all of a sudden you've got someone in the office who is maybe highly tooled, right? So this is what you're talking about. Highly tooled, but who has access to knowledge that other people might not have. And the problem becomes, I mean, that then becomes a potential problem for an office in terms of, are you going to run the office one way or run the office another way? And I remember actually I used to work at SOM, and one of the most influential discussions that was at SOM that for me was an informal lunchtime lecture where they brought in Robert Diamond, no? He was the partner who did the Hancock building back in the 60s. You were there. Were you that lecture?
Bruce Graham and also Cobb.
Okay. Well, from my memory of the lecture, he was the main partner sort of looking over that. Maybe not the design partner, maybe the managing partner. But he gave a lecture about computation and the role that it had at SOM, the power structure of the company. And as an ex-SOMer, I guess I can say this. But so, you know, design used to happen here, and then they had the technical people here, and the designers would draw something, they'd pass it down here, these guys would change it, they'd pass it back up here, and it's like change, right? And it's when they developed the tools that you used to work with, and you guys should be telling the story, not me, because you're the first-hand people. But they developed the tools, all of a sudden it changed the way, right? And so this is another example of the power of tools, where all of a sudden they said, we're going to develop multidisciplinary teams. They're all going to fuel this algorithm so that overnight, all of this really expensive computer time, because it was super expensive back then, could be used effectively. Because if you get the wrong information in, garbage out. And it changed the nature of their teams, and then it changed the culture of the office. So they became this really extremely interesting place to be, which you still are. Right? And I mean, that's really cool. And the other thing he said is that the hidden side effect of all of that is it opened up a whole new client. The developer became a feasible client, because all of a sudden you had a technology that could let you respond to clients much more quickly, and right, as we are all suffering that today. So I mean, that's that's kind of what you're talking about. Maybe it's not happening today quickly enough, but it happened at one point. If you get the right people in the room together, it'll happen.
I think it is. That's the really interesting part of the profession right now. It's going through that resurgence again, because you have young people who are really facile at using.
Yeah, but I still find that we have students that are very facile at the end, students that are now in their 4th or 5th year, and those students are not those same tools that are facile with the knowledge of physics or the ability to compose elegantly. And so I think one of the things that's interesting about what you're doing with the kind of more embodied approach is that they're both that immediacy. They now have the knowledge and they have the tools. That gap isn't there, and I think there's still a big gap. I mean, there's a gap in terms of the studio faculty driving the studio and those faculty who are sort of teaching the tools. And the goal, of course, is to bring these closer together. But I feel like there's still a resistance.
Do they have to exist in a single person, or
no? Absolutely, they don't. Like if you have the knowledge, how do you get the knowledge into the right hands, into the right drivers, and how do you partner that together? That's the ultimate challenge.
Good time to break from here.
Yeah. Thanks again, you guys, and thanks TT for hosting.
Thank you.
One